now. Right. And Josh, please take it away. Thanks.
Yeah, thanks so much, Sam and Seth, for the invite. I'm very grateful to be speaking to you all. And thanks for the anonymous time at 11 a.m. Hopefully you won't find it too strange. So today I'm going to talk about Monte Carlo twisting for particle filters. And this is some work that I did during my PhD, and I'm still kind of working on, or definitely still working on now, trying to get a few things ironed out, but I'll take you through where I'm currently up to. So this is joint work with Anthony at Bristol and Christopher Vandy at QUT. I was supported by the School of Mathematics at QUT and the Center for Data Science. If Twitter is around much longer, you can hit me up at BondStats. Otherwise, email is fine. And the paper, a version of the work is out on arXiv, but it will be updated in the next month or two, I'm guessing. So my research area is adaptive methods for sequential Monte Carlo, and these methods, ones that are where you tune your SMC sampler with the particles. So it's at least my main research area. I'm getting into some other things like approximate Bayesian stuff now. And this work is for particle filters for dynamic models where the transition densities, so the Markov kernels, are difficult or at worst completely intractable. So you can't write down what the density is. And therefore you can't do any reweighting or anything fancy that you'd normally do with SMC. A bit of the motivation. So we often talk about hidden Markov models. And there's two main things you want to do with hidden Markov models. It's either inference over latent states. So in robotics, that's often like having a drone and having it localize itself in space, figure out where it is. So you don't know where you are, but you use observations in order to localize yourself within space. In finance, often there's like a time series type style analysis where you have a latent state that's unknown, but observations that are related to it, and you want to kind of find out the most likely states. And some work that I am currently doing, which is pretty cool in psychology, is trying to model internal decision-making processes using these latent states, and then use observations of time a decision was made and what decision was made to kind of inform what those decision-making processes, or at least a model of those decision-making processes, look like. So that's what you use particle filters for on hidden Markov models for the latent states. But of course, also it is also useful, very useful for unbiased estimates of the normalizing constant associated with these models. And that includes pseudo-marginal methods for like Markov chain Monte Carlo, and also model selection. And that comes down to estimating this normalizing constant, which is an expectation of a series of potential functions where you don't know what the latent state is. And the really cool thing about particle filters is they're very well adapted to hidden Markov models in the sense that they exploit the conditional structure. So I find that really interesting. So here's a slide on notation, but instead of calling it notation, I much prefer to have a somewhat tongue-in-cheek title. So everything is an integral, rainbow. So I'm going to talk about probability distributions or probability measures on some measurable space, and I'll talk about taking the measure of sets within that space, and also talk about taking the measure of particular functions in that space. And I'll write down some distributions or measures that are defined implicitly when I do some kind of reweighting of the measure. But I'm pretty sure everyone here should be well versed in this type of notation. But please do stop me if I'm losing you on something. But if it is just on the real line, you can of course write these things down as just standard integrals from calculus of density functions. So if you don't like this, you can always switch to densities relatively easily. I'll also be talking about Markov kernels a lot, so a non-negative kernel on some measurable space. And again, I mean, there's lots of ways to think about these things, but the way that I like to think about it is just for a fixed V that's in the space, I essentially have like a conditional measure. So once I know what that V is, I'm outputting a particular measure. And there's some fancy notation where you take like the kernel of a function, and then it itself becomes a function because it's conditioned on this V. But basically, it's a really neat way of having notation such as this mu of k of phi down here. Okay, so Feynman-Cach models are the models that underlie how sequential Monte Carlo operates, and it's the mode with which we analyze these algorithms' properties. And for particle filters on like dynamic Bayesian models, they align really nicely with the hidden Markov model example I gave at the start. So I'll just go through what a Feynman-Cach model looks like for one step first, just to give you a bit of a, I mean, this might be a refresher for some people, or it might just be dead boring. But if you start with an initial distribution here, e to naught, same as m naught, and you have a potential function and then a Markov kernel, essentially you're updating your initial distribution with a potential function. So you're doing some kind of reweighting step on this distribution. That gives you an updated measure, which we use this hat notation for. And then we use a Markov kernel to propagate the distribution forward. So a convolution type, or a convolution of the distribution. And so if a Feynman-Cach model for multiple steps is just repeating this process multiple times. And all the particle filter is just, instead of propagating the distributions, you're propagating a set of particles. So you start with draws from your e to naught, you reweight them using the potential function. That gives you an estimate of the updated distribution based on importance sampling ideas, and then you propagate those particles forward using the Markov kernel M again. And eventually you get a set of particles that approximate your predicted distribution there at the end. When we do this multiple times, it's really nice to write down as a recursive definition where we're using this gamma here as the unnormalized predictive measure, which takes the previous unnormalized predictive measure, updates it with this reweighting step, and then propagates it forward. So it's just a really neat way to write down a definition for a Feynman-Cach model. And we can do the same thing for the updated counterparts. So these are these hat guys, and it's essentially we just take the predictive measure and we reweight it with the next potential. And of course, we've got our normalized versions there on the right. So just a quick summary, we can define the Feynman-Cach models essentially with a set of Markov kernels and a set of potentials, where of course the first m naught there is actually an initial distribution, not a Markov kernel. And we'll use these hats for updated, we'll use eta for the measures, and we'll use gamma for the measures, and we'll use eta for the distributions, just as like standard notation. So the Feynman-Cach model defines a path measure or distribution. It defines the sequence of marginal distributions, and it also defines how we traverse these. You can set up an infinitely many number of models to perform the same statistical inference, but there are many bad models for SMC in terms of the variance of the estimates you'll get for the functions or latent states that you're interested in estimating. So the question arises, how do we improve an existing Feynman-Cach model for use in SMC? And that's where twisted Feynman-Cach models come in. So just to revisit twisting, if you take some distribution and you reweight it with this psi function, essentially, so long as you can take the measure of that function, then you've essentially defined a new distribution that's been reweighted according to that function. So exponential twisting or tilting is the usual example where you're just adding this exponential weight with some parameter lambda. It'll define a new density, and it's essentially just a change of measure by reweighting. And you can do it so long as you can find what the new normalizing constant should be to make sure that it's a valid probability measure. So for a twisted Feynman-Cach model, essentially what happens is you now have a set of potentials and Markov kernels that have been twisted, and they define these intermediary distributions, these marginal distributions that are also twisted. So you start off by twisting the initial distribution. So this could be either naught to this psi, but it could also be the m naught notation is also fine. And if you do it in such a way that is optimal, you can make it so that the potential functions are just one. So essentially you can remove all of the weighting or reweighting that you have to do, both in the Feynman-Cach model sense, but also in the particle filter sense. And the nice thing is that you'll end up preserving the path and terminal distribution. And as I said, under the optimal twisting functions, the potentials will be constant. So this is just a simple example for the one step. Same holds for the particle filter version. And if your potentials are one, you don't need to do any resampling. And the really cool thing about that is essentially you end up with a sequence of Markov kernels, starting with an initial distribution, where all the potentials are one, and you know that you're targeting the correct terminal distribution. So therefore, you're doing exact sampling from what your terminal distribution should be. So just to
clarify, in this optimal setting, that basically corresponds to taking C equal to the potentials, right? Is that right?
Taking what equal to the potential? Sorry,
like the twisting C is basically equal to the potential. Is that right? Or not quite? As in, you said in the optimal case where your weights end up, your potentials end up being one. Is that because you've basically taken the original potential to be your kind of twisting C function?
Yeah. In this one step example, yeah, exactly. Yeah. So you've kind of absorbed the potential into this first distribution with the twisting formula that I gave before.
Right.
And then all of a sudden you don't need to do any reweighting because you're already incorporated that reweighting into your exact sampler.
Right. Got it. Yeah. Yeah. Thanks.
That's a good clarification.
And just to confirm, as of now, we haven't decided how to pick psi. We just have a psi fixed, or is it the psi change with the along the path?
For this example, I'm just telling you what the good psi is.
Okay.
I've given the good psi for free, and you haven't even had to do any work. Yeah.
Thank you.
So if you compare these two, the samples that you end up for the predictive distribution at the end, the base samples from using the base Feynman-Cach model won't be exact, but samples from the twisted version where I've chosen the optimal twisting function, they will be exact samples from this n-2 distribution. So, okay, we can twist a one-step Feynman-Cach model, but how do we twist multiple? Well, there's a really elegant formula here that says you twist the initial distribution as you would expect. So it gets twisted by this psi naught. And then for all subsequent Markov kernels, you twist again by this psi naught. But this m naught psi naught here is just a constant, but here it's not a constant. So it's going to change the Feynman-Cach model if you don't do something to correct for it. And that's where the twisted potential functions come in. So if you define your potential functions in this way, this term here will cancel out with the denominator here perfectly, such that you'll preserve the terminal distribution and the path measure. So there's a way to construct a twisting of an entire Feynman-Crack model that preserves the quantities that you'd like to perform inference on. And once you do this, so once you like find what the twisted Markov kernels are, and once you find what the twisted potential functions are, you can push it, or you can run this Feynman-Crack model, or you can estimate the latent states of this Feynman-Crack model using just a standard bootstrap particle filter. So there's nothing extra that's needed. You're just changing the underlying model. And so, yeah, like I was saying, if you write all these twisting things down, all of these twisting things like cancel out, essentially. It's not a hard exercise. And it will preserve those terminal distributions and terminal quantities, but it won't preserve the intermediate distribution. So you do lose something. It's not exactly for free. If your intermediate states are of interest, you haven't exactly gotten away with everything for free. So now let's talk about, well, if I've got all this flexibility with this twisting of the Feynman-Crack model, what function do I want to choose? And it's the function that incorporates all future information from your potential functions. So given the state that I'm at, I would like to find the expectation of all of the potentials for like all the paths forward and weight according to that. And if I can use this twisting function, then I will guarantee that I get a particle estimate of the twisted normalizing constant that is equal to the normalizing constant of the model that I'm interested in, and that's for any n. So I could use n equals 1 if I had the optimal twisting functions. And I would also get exact samples from the terminal distribution if that was the case. So if I could actually analytically solve this optimal twisting function. But of course, that's just as difficult as the estimating the Feynman-Crack model using a particle filter in the first place. So it's not yeah, we're still stuck. You still have to do something. So that's where the iterated auxiliary particle filter and controlled SMC came in. So they use this recursive definition of the optimal twisting functions, which is start the terminal twisting function at the last potential, and then update each successive one by the expectation of the next optimal twisting function conditioned on the value that xp and multiplied by the potential at that time. Which this kind of like form of the optimal twisting function motivates a recursive learning algorithm for them. So if you have your twisting functions in some class, you can run a particle filter, like a bootstrap particle filter with the current twisting function and generate a set of particles for all the times along that Feynman-Crack model. And once you've got the all those particles, you can use this recursive definition to do essentially a regression to find out what class you should, or what element of the class H you should choose that best represents your current twisting function, or your current estimate of the optimal twisting function, given the estimate that you just learned in the time step p+1. And so you can iteratively, I guess, make better and better approximations of the optimal twisting functions with this kind of algorithm. For this to work, the twisted mutation kernels need to be sampled from exactly, and the normalizing constant needs to be able to be calculated analytically. So that restricts like the class that's been currently looked at in iterated auxiliary particle filters and controlled sequential Monte Carlo to one where there's some kind of conjugacy, and they've looked at using like normal distributions for the Markov kernels and exponential quadratics for the twisting function. So essentially Gaussian and Gaussian. Because the twisted mutation kernels can very easily be sampled from, and the constant can be readily calculated. So most methods use this. The iterated auxiliary particle filter also does mixtures of normals as well. So beyond just the exponential quadratic, it does a mixture of exponential quadratics. But yeah, all these methods are essentially relying on some kind of conjugacy, and they almost solely focus on the normal case. So this work is about going beyond this exact twisting setting. So like, what if there's no class of appropriate twisting functions that are tractable, and that may be that the underlying Markov kernel is intractable or difficult to work with. Maybe it's something that you can't write down the density for, or maybe the class of twisting functions that you want to use define a twisted Markov kernel, which you also don't know how to sample from directly. Well, the idea of this work is to use a rejection sampler to handle the sampling from the twisted Markov kernels, and then use an unbiased estimate of the twisted potentials, because those twisted potentials involve an integral with respect, or involve an expectation with respect to this intractable Markov kernel. So we also have to take care of that. So the rejection sampler is pretty simple. If you restrict, so long as you can find like an upper bound for your twisting function, you will be able to restrict it to 0, 1, and then you can use like a simple rejection sampler like so. And when you accept a realization, or even if you accept a realization, if you don't have some kind of lower threshold on the twisting function that you're using, it will have the correct twisted distribution. And then for the unbiased estimate of the twisted potentials, if you recall the definition of the twisted potential function, it's essentially the original potential function divided by the current twisting function. But now we have this expectation of the next twisting function. And so because we're assuming this Markov kernel is intractable or difficult to work with, we want to come up with a way to estimate this expectation. And a very natural way to do that is just to sample from the underlying kernel. So that's this part on the right-hand side here, conditional on the state that you are at, and then evaluate the function at that state and take the average, or if k can be 1 through to whatever finite number you want to use. So this kind of idea is applicable to any Feynman-Kac model where you have a bounded psi function, and where the underlying mutation kernel can be sampled from. And like I said before, it's a rejection sampler for the twisting mutation kernels, which means that it's exact twisting, but it could be potentially quite costly. And you've got a Monte Carlo estimate for the difficult part of the twisted potential function. So that's a really simple thing, but it's potentially could be noisy. So you've got something that's costly and something that's noisy. So how do we address those two concerns? And that's, I guess, what the meat of this project was about, is like, how do we do that in sensible ways? So for controlling the cost of the rejection sampler, the acceptance rate of such a rejection sampler looks like this. So it's the expectation of the functions, so that I've changed the twisting functions to be omega here, of omega, conditional on the value that you currently are at. And if I wanted to know what the average acceptance rate is, I would need to average that over all the probabilities associated with the particle set I'm drawing from, or the distribution I'm drawing from, to get xp minus 1. And that work turns out to be this updated eta, this twisted updated eta at p minus 1. So that's like the inside the particle filter. When I do the rejection sampling, I would expect on average to have this alpha omega p acceptance rate on average. and the alpha naught is a bit simpler. It's just evaluating the initial distribution at the twisting function. Okay, so that tells me what the acceptance rate is in terms of the twisting function that I want to use, but I need to change that twisting function before I run the particle filter in order to control the computational cost. And that's where it gets a bit sticky, but luckily we were able to come up with this, I guess, this different expression for the average acceptance rate, which you'll note is if I start with, so let's say currently I'm at this psi-twisted Feynman-Cach model, but I want to know the average acceptance rates for an omega-twisted model, then I can calculate that acceptance rate for the omega-twisted model using only things to do with the psi-twisted model and the twisting functions which I will have, like I have those twisting functions. And if you've got this kind of form, then if you've already run a particle filter, you've got access to estimates of all of these things, or you can generate estimates of all these things. And it means you can change the omega, you can like fiddle with the omega in order to control what the acceptance rate, or what the average acceptance rate the estimate of the average acceptance rate is going to be. So yeah, you can estimate it without running the actual model that you're interested in, so long as you've got access to a previous model. So yeah, and we want to, the idea now is to target the acceptance rate in this iterative learning algorithm and temper the new twisting function, so have like a inverse temperature value on the twisting functions in order to boost that acceptance rate to something that's more acceptable. And so the proof for this proposition, this result, is essentially if you decompose the twisting functions into the old twisting function with some residual, and you use these nice properties that if you have a updated side twisted marginal and then you twist it again, it just becomes you're just twisting the marginal with respect to the product of those two things. And the other one being, if you look at the phi twisted updated marginal, then you can expand it out like this. And it yields a result which essentially gets rid of this omega, except for its influence on the residual. And then you can use it to express that acceptance rate without the omega twisting after you do some algebra. So this is how you control how you can control the cost of the rejection sampler within the particle filter. The other difficulty was we wanted to know what the effect of using the random weights is. So if you consider a Feynman-Cach model that's got this as defined by this series of Markov kernels and potential functions, and then you've got another model where the G bar is to denote the fact that it's an unbiased estimate of G, and you've got marginal measures that will coincide, but I've used different notation there. If I want the asymptotic variance of the terminal expectation of this var phi function, then it'll have, just by standard results, it will have this form where it's the sum of these VPNs. But if instead if I use this unbiased estimate, then it works out that these VPNs can be written as you typically would. So this is almost the expression that you would normally get, except for this SP function that's here. And SP here is the relative second moment of the unbiased potential functions. So if SP is equal to 1, which would coincide with you using, not estimate of G, so just use G bar P is equal to GP, then you would recover exactly the asymptotic variance formula that you get from standard results in SMC. But here we're using an unbiased estimate, so the SP, based on how variable the unbiased estimate is relative to the true potential function, it will inflate the variance somewhat. And the sketch of that proof is you define your Feynman-Cach model on an extended space. So it'll have X and U now. And this will be to represent, the U's will be used to represent the randomness that goes into the estimate of G bar. And you set up what the asymptotic variance typically is. The steps are, you need to relate the QPNs. So these are the typical thing that go into the asymptotic variance calculation. You need to relate the QPNs for the augmented model to the augmented model, which represents using an unbiased estimate, to the QPN for just using G, using a ratio of the augmented potential to the standard potential. And then essentially, like this expression here, relate the augmented model version of that to the standard version by taking this and taking an expectation, or taking the second moment of it. So there's a bit of algebra there, but like once the steps are clear, it's not, I mean, at first I found it a little difficult, but you know, it's one of those things where you stare at it long enough and you get a bit more comfortable. And the nice thing is that the effect of using like this unbiased estimate is asymptotically like isolated to each VPN. So the SP, if we go back to the formula, is related to the VPN, which is related to the time P, the asymptotic variance associated with the time P part of the particle filter. So there's no, at least asymptotically, there's no compounding of variance by using an unbiased estimate of the potential function. From that formula, you can come up with a uniform bound for using the unbiased estimate based on like the asymptotic variance of an estimate of the function var5 from the particle filter at the terminal measure of the particle filter. And it just says if you can bound all of those SPs, so they were the relative second moments, by some constant C plus 1, then for centered functions, so that's what that condition is, for centered functions, you can bound the variance related to the particle filter with the unbiased estimate by the original variance, but multiplied by the C plus 1. And for the normalizing constant, you get almost the same thing, but because it's not centered, you have this additional n, where n is the number of steps in your Feynman-Cach model times C. So just an example on a linear Gaussian hidden Markov model. So this is dimension 3. Number of steps in the Feynman-Cach model is 200. Everything is, all the covariances for the Gaussian part of the model are diagonal, and we test with two variances of the potential function. So 0.25 and 1. And because we wanted to test how it worked on a simple example where we could actually calculate what the normalizing constant should be, we chose this setup. And we chose from the class of exponential quadratic twisting functions because they should be enough to, they are like that family is large enough to define the optimal twisting functions for this particular model. And we tried, so this iterative learning procedure over 3 iterations where we lowered the acceptance rate target from 0.04 to 0.02 to 0.01. We use 200 particles for the twisted models. Dynamic multinomial resampling. And then to calculate the unbiased estimate of the potential functions, we use 25, 50, and 100 samples. And so we did this over 100 repetitions. So these are new data sets. And sorry, these are new data sets. No, the same data set for each plot. And we compared it against a bootstrap particle filter that used the same amount of memory as our algorithm, and then a bootstrap particle filter that used the same number of computation, where we measured computation by the number of mutation draws from this. And the results were interesting, not as great as we had hoped, but still promising in terms of definitely the validity here of the method is shown off. But essentially, if we read from top to bottom, we've got the optimal the auxiliary particle filter, so like I guess the twisted Feynman-Cach model with side twisted, where we've given it the optimal twisting functions, but we have used our method to change the acceptance rate so that we target a particular acceptance rate and control the computational cost. And then we've got doing all of that, but also learning what the twisting function should be for 1, 2, and 3 iterations. And then we've got 2 particle filters where we do no twisting, but one has this equal storage and one has this equal computation cost. And so like the equal computation cost wins every time. It just does a lot better for this particular example. But we do in some cases almost as well, if not better, than what the optimal twisting function should be after changing the acceptance rate. So if you could just compare the top 2 distributions of every facet, you can see that we're sometimes beating it in terms of its estimate of the normalizing constant, and sometimes doing just well here. Maybe we did it like a little bit worse. So yeah, it's shown some promise there. And it absolutely blows the equal storage cost bootstrap particle filter out of the water, which could be interesting for particular applications where there's some kind of storage constraint, or if the storage is the cost of storage is actually what's slowing down what your computations are. If there's some kind of memory allocation is causing it to be a slow algorithm.
So is the interpretation of why the storage thing is relevant, is it just that instead of doing rejection sampling, I could have just kept all those samples and importance sampled them, basically? Is that how I should be thinking of it as comparing?
Yeah.
Great, thanks.
So there's one other extension that we looked at where we kind of relaxed our condition on the rejection sampling. So before we assumed that all we could do, the best we could do was rejection sampling. But now we assume that there's some kind of like partial twisting that you can do. And that's where we assume that if we were to decompose the twisting functions that we've learned into this rho and omega, then an exact sampler for the twisted version of the Markov kernel M exists for the rho part, but not for the rho times omega part. And so we exact sample from the part that we can do the twisting for analytically, the Markov kernel that we can actually do the twisting for. The twisting function, the part of the twisting function we can actually bring into the Markov kernel to do exact sampling, and then use rejection sampling for the remainder. And the idea is to choose that row so that we can maximize the acceptance rates. So we did this for a stochastic volatility model, which has this SDE representation here. And if you for this particular stochastic volatility model, you can show that unit increments of the xt follow a non-central chi-square distribution, and therefore, after you do some work, it's in the appendix of the paper, you can show that it can be exponentially tilted. So we did this example for, or maybe I should refresh you on what the algorithm is actually doing. So you run the particle filter just with the base particle filter, and then you learn what the optimal twisting functions are based on that. And then after that step, you try and do this decomposition of each of the twisting functions you learned in order to take some of the twisting function into the Markov kernel so that you can do exact sampling with, such that you are maximizing the acceptance rate. And if you boost this acceptance rate, essentially you're going to have a particle filter that's less costly because you've got less rejections that you have to do. So this is for a time series of length 2000. We generated the data with these parameters, but then we changed the parameters that we put into the Feynman-Cach model just to make them not exactly the same. And we use exponential quadratic twisting for the rejection part, and then like an exponential linear, so like a exponential tilting type change of measure for the analytical or the partial twisting part of the algorithm. We just did 2 iterations of iterative learning with the number of particles equal to 100, and the final twisted particle filter we had n equals 250. And apologies for this graph, I recently changed it, but essentially it's trying to show that this final like 2 iterate learned twisting function, where you do this step of trying to optimize the acceptance rates, has a much better estimate of the log normalizing constant. So the top line is better than the comparative storage and comparative computation estimates of the normalizing constants. And so like ongoing work right now for me is to test parameter estimation within a pseudo marginal Markov chain Monte Carlo algorithm. So to try and take this, but now change it to be used as part of like a larger algorithm, which most of you will have guessed. So just in conclusion, I guess from the start of the talk, what I really wanted to get across was these twisted Feynman-Cach models are really interesting because if you can find, of course you can't, but if you could find what the optimal twisting functions were, you would define perfect samplers. But that's nice because it gives you something to target in terms of trying to find like the best Feynman-Cach model out there. And this is something that I'm that doesn't sort of have a direct, at least a direct counterpart in Markov chain Monte Carlo. Currently, like before this work, the analytical twisting was limited to only a few models because you had to rely on this like essentially conjugacy argument in order to get them to work. We extended that with rejection sampling and with random weight SMC. Did some work to make that kind of be practical for the models that we have tested so far, and that partial rejection options, so this like partial analytical twisting may be available, but we've only tested it for 1 model so far. And so current and future work is, like I said, the pseudo marginal MCMC stuff, test it on new models, and also kind of come up with some recommendations for when you would or wouldn't use this type of approach. So obviously, or not obviously, but we kind of restricted this work pays attention to the intractable Markov kernels or models with intractable Markov kernels. And if your Markov kernel is not intractable, then you will do a lot better to find probably other methods, because you're really between a rock and a hard place when your Markov kernel is intractable for doing like approximate exact type inference. The archive's there if you want to go look at where we're currently at, what we've currently put out there. But I just want to say thanks for listening. Yeah.